Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. In lecture number 44, we have discussed how to solve integral equation using Laplace transform. In this lecture also, that is lecture number 45, we will discuss one more example on solving the integral equation using Laplace transform. I suggest you to watch lecture number 44 first before going for this lecture. In lecture number 44 we have discussed what is integral equation and how we can solve integral equation using convolution theorem for Laplace transform. In this lecture we find out solution of this integral equation using Laplace transform. So first we write down the given integral equation and then we try to solve it using convolution theorem. So given equation is y of t equal to 1 plus integral from 0 to t y of u integral with respect to u. Now first step is to express this integral as a convolution of two functions. So you can see, if I consider convolution of function y with constant function 1, suppose I find out y star 1, then by the definition of convolution this is going to be 0 to t value of y at u, which is y of u, and value of this constant function at t minus u, and because function is constant, its value is 1 at every point. So this is nothing but integral from 0 to t y of u du. If you remember the definition of convolution of two functions f and g, then it is equal to integral from 0 to t value of f at point u and value of g at point t minus u. In this definition we consider f of t equal to y of t and g of t equal to 1. Therefore f of u equal to y of u and g of t minus u is 1, because g of t is 1 for all t, therefore g of t minus u is also 1. Therefore we can write this integral from 0 to t y of u du as convolution of y and 1. So in the next step we replace this integral by y star 1, and we mention in the bracket that because y star 1 equal to integral from 0 to t y of u du. Now we consider Laplace transform on both sides of this equation. Therefore Laplace transform of y of t equal to Laplace transform of 1 plus Laplace transform of y star 1, that is equal to Laplace transform of 1 plus Laplace transform of y star 1. This we are writing using linearity property of Laplace transform. Laplace transform of addition equal to addition of Laplace transforms of two functions which are in the addition. And we denote Laplace transform of y by y bar s, because y is unknown function which we want to determine. We don't know what is y of t. Therefore we denote Laplace transform of y of t by y bar s. Laplace transform of 1 is 1 by s, and Laplace transform of convolution equal to product of their Laplace transforms, that is Laplace transform of y into Laplace transform of 1. Here we are applying convolution theorem for Laplace transform. Laplace transform of convolution of two functions equal to product of Laplace transform of those two functions. Therefore y bar s equal to 1 by s. Laplace transform of y is denoted by y bar and Laplace transform of 1 is 1 by s. Therefore, we have y bar of s divided by s. We are interested in y bar s, so we consider this term on left hand side and we take y bar s common, so that we have 1 minus 1 by s times y bar s equal to 1 divided by s, and this we can rewrite as s minus 1 divided by s y bar s equal to 1 by s. Therefore, y bar s equal to 1 by s into s divided by s minus 1, and finally y bar s is 1 divided by s minus 1. We cancel out s here. So we have Laplace transform of y of t, which we have denoted by y bar s, and to obtain y we take inverse Laplace transform on both sides of this equation. L inverse of y bar s equal to L inverse of 1 divided by s minus 1. L inverse of y bar s is y of t, and L inverse of 1 by s minus 1 is e raised to t. So this is the solution of given integral equation, which is solution of given integral equation. So it is easy to solve integral equations using Laplace transform if it is possible to express the integral of given equation in terms of convolution. Here we are able to write this integral as a convolution of two functions y and 1. Therefore, we are able to solve this integral equation using Laplace transform. Not every integral equation can be solved using Laplace transform. There are some special types of integral equations which we can solve using Laplace transform, and those equations are that type of equation in which we can write integral in terms of convolution, so that we can apply convolution theorem. We can have one more example related to this. We try to solve this integral equation y of t equal to t times e raised to t minus 2 times e raised to t e raised to minus u y of u du. So here we require t minus u. Here, if we recall the definition of convolution of two functions f star g of t, then we have 0 to t f of u g of t minus u du. So here we can consider f equal to y, so that we have f of u equal to y of u. If we take f of t, if we consider f as unknown function y, then f of u will be equal to y of u. But here we require t minus u, g of t minus u, or value of function g at t minus u. So for that we can see here variable of integration is u. Therefore t will be considered as constant. Therefore we can consider this e raised to t inside the integral. So first step is we rewrite our integral equation by taking this e raised to t inside the integral, and we will have e raised to t into e raised to minus u is e raised to t minus u, and here we write y of u du. Now if we take f of u equal to y of u, or f of t equal to y of t, and g of t equal to e raised to t, then g of t minus u will be equal to e raised to t minus u. So you can see this is nothing but convolution of function y and function e raised to t. F of t is y of t, g of t is e raised to t, and then we have y of u equal to f of u, g of t minus u equal to e raised to t minus u. Therefore we have convolution of function y with e raised to t. So that we can now write as t times e raised to t. This we can write as convolution of y and e raised to t. Therefore y of t equal to t e raised to t minus y star e raised to t, and we can mention in the bracket by the definition of convolution y star e raised to t equal to 0 to t y of u e raised to t minus u, integral is with respect to u. In the next step we apply Laplace transform on both sides. Therefore Laplace transform of function y equal to Laplace transform of e raised to t into t minus Laplace transform of y star e raised to t. So here we apply linearity property of Laplace transform. Now to obtain the Laplace transform of e raised to t into t, we can apply first shifting theorem, and we know that Laplace transform of t is 1 divided by s square. Therefore Laplace transform of e raised to t into t will be equal to 1 divided by s minus 1 whole square. We replace s by s minus 1 because we have e raised to t in the product of t, and Laplace transform of t is 1 by s square. And here this is by convolution theorem Laplace transform of y into Laplace transform of e raised to t. So let me write this in the bracket. We are applying two results, first shifting theorem and convolution theorem. By first shifting and convolution theorems, using these two results we are able to write down these two Laplace transforms. Now we rewrite all these things again. We want to find out value of y bar s first. So I keep this as it is, 1 divided by square of s minus 1. Laplace transform of e raised to t is 1 divided by s minus 1. Laplace transform of y is denoted by y bar s, and we are interested in y bar s, so we consider this term on left hand side and we take y bar s common, and we can rewrite in this way: y bar s equal to 1 divided by square of s minus 1. Now we simplify this, we take s minus 1 LCM, and here we have s minus 1 plus 1 y bar s equal to 1 divided by s minus 1 square. Therefore s divided by s minus 1 times y bar s equal to 1 divided by s minus 1 square, and therefore y bar s is 1 divided by square of s minus 1 into this quantity, that will be reciprocal here, s minus 1 divided by s. Therefore y bar s equal to 1 s minus 1 will cancel out, and we have 1 divided by s into s minus 1, and we require inverse Laplace transform of this. And if we observe, if we take the difference of these two, we have s minus s plus 1, and this s will cancel out, so we can write this 1 as the difference of s and s minus 1. Okay, this we are doing for obtaining inverse Laplace transform of y bar s. Therefore y bar s can be written as, now we consider s divided by s into s minus 1, so s will cancel out, and minus s minus 1 divided by s into s minus 1, so s minus 1 will cancel out. And now we take inverse Laplace transform on both sides. inverse Laplace transform of y bar s equal to inverse Laplace transform of 1 by s minus 1 minus inverse Laplace transform of 1 by s. Inverse Laplace transform of y bar s is y of t. Inverse Laplace transform of 1 by s minus 1 is e raised to t, and inverse Laplace transform of 1 by s is 1. So this is the solution of given integral equation. It is y of t equal to e raised to t minus 1 is the solution of given integral equation. So you can see it is very easy to obtain the solution of integral equation in certain cases if we are able to express integral inside integral equation as convolution of two functions. So once we are able to write down our function in terms of convolution, then we have to apply Laplace transform. Once we apply Laplace transform, we have to find out y bar s after simplifying all these things, and once we obtain y bar s, we have to find out inverse Laplace transform of y bar s, which is y of t. So I think we have done enough number of problems on integral equation. So in the next lecture we will start with a special type of function which is known as unit step function, and it is very helpful in the topic of Laplace transform. So this we will discuss in upcoming lectures. Thank you very much.